Welcome to the UEI Technical Masterclass. I hope everyone's doing well today and weathering this current pandemic. I'm Bob Finn with UEI, and today's webinar is entitled Understanding the MIL-STD-1553 Bus Controller. This is the third webinar in our month-long focus on avionics. Today, we'll take a detailed look at the bus controller and bus writer functions in our MIL-STD-1553 I/O board. This is not only a presentation of technical information, but an opportunity for you to interact with our application engineering team. Just fire off any questions you have using the webinar chat tool. And please don't be shy. And so without further ado, I'm going to turn it over to today's presenter, Phil Zavitas.
Welcome to the 1553 Bus Controller Masterclass. MIL-STD-1553 has been deployed for over 40 years, starting out on the F-16 and now being used in space. The reason is it's simple, deterministic, and reliable. A 1553 system will have a bus controller, will have up to 32 remote terminals, and each remote terminal will have 32 subaddresses. An example of a remote terminal might be a missile launcher, and the subaddresses may be the missiles. And then there's an optional bus monitor that allows you to observe and even record the traffic on the bus. The system has two sides to the bus A and bus B for safety and redundancy. Every RT is connected to both sides of the bus. The bus controller has responsibilities, and these responsibilities lead to the reliability of the system. The bus controller initiates message transfers on the bus. Only one active bus controller is allowed, and it sends commands in a predefined pattern. It's responsible for receiving the status word from an RT after it sends a command to check different bits, and one of those bits is the message error bit. Again, this handshaking leads to the reliability of the system. The bus controller will send a command on one side of the bus, say bus A to start with, and if it doesn't receive a reply in a certain amount of time, it's responsible for trying on the other side of the bus. The bus controller needs to service any requests that come from the remote terminals. The remote terminal can optionally set a service request bit in the status word, and it's up to the system designer to specify what should happen if that bit is set. And the bus controller needs to detect and recover from errors. A fighter aircraft is a complex system. There are components that are more critical than others that may need to be communicated with at a higher frequency. So it's not a linear system. We need to deal with multi-rate commands. Some of the commands you would see on the bus is a BC to RT command, where the BC sends data to the RT, maybe a firing command, or the BC requests data from an instrument. Or it can combine those two and allow an instrument to send data to another RT. That's an RT to RT command. There are standard words in a 1553 system. There's a command word, and you'll see the terminal address, the RT, the subaddress, a word count, and whether it's a transmit or receive command. Data words are 16 bits. Status word comes back from the RT and has the remote terminal address. It might have the message error set or cleared. Let's take a look at a transaction on the bus. A BC to RT command will have the command word. So we're sending data to the RT. So there's a command word and data going to the RT, and the RT replies with status. You can see here it's the RT number and a clean status, no message error bit set. An RT to BC command means the BC is requesting information from the RT. So it sends a command, and the RT replies with status and data. If we break the command down, you'll see the hex code translates to RT8, receive, SA8, 4 data words. And you would see 4 here in the word count, 8 here in the subaddress, 0 indicating receive, and 8 in the RT. Likewise, if we break down the status word, you'll see the terminal address here, which is 8, and no message error. There are common commands that are transactions between one or two entities, a bus controller and a remote terminal, or maybe between a bus controller and two remote terminals. There are also broadcast transactions, a one-to-many relationship. We've gone over these commands. There are mode code or mode commands. These are designed to allow the bus controller to control the RT itself. Some of the things it may ask the RT to do is shut down or initialize a self-test. Here's a list of mode codes. The RT has the ability to set the service request bit, and the system designer will decide what the bus controller's responsibility is if that bit is set. And that's in the status word, located here. Again, this is optional. The standard also allows for a backup bus controller. So the system may turn control over to a backup bus controller for intentional purposes, maybe maintenance. During a mission, if there's an issue with the current bus controller, the backup bus controller must take over. That might be on a predefined sequence. Maybe there's no traffic on the bus for a certain period, in which case it will take over. And if there's more than one backup bus controller, the highest priority backup bus controller goes first. The bus controller must monitor the traffic for errors. It's in charge of the bus communications. It needs to know if there's an early response, a late response, or no response at all. It needs to verify if there's too many words or too few words in a message. The UEI 1553 I/O board has 2 channels, and each channel is an independent 1553 system. It can have a bus controller, a remote terminal, a bus monitor, or you can add a bus monitor to either one, the bus controller or the remote terminals. And you can duplicate this, given that they're completely independent channels. You could have 2 bus controllers running on one I/O board if you wish. How to send a command. We have 2 ways, and one is the bus writer, and one is a MajorMinor frame scheduler. The bus writer uses a FIFO to send commands. It's very easy to use. It allows you to send 1 or more commands at a time. You simply call the API, and the commands will be sent on to the bus. It is not designed to handle error checking, retry on a different side of the bus. It is a very simple method to send commands. Maybe you need to send 30 commands to test an RT, and you just simply need to call this 30 times with commands. As I mentioned, 1553 systems deal with complex problems, multi-rate problems. So to handle this situation, we have the MajorMinor frame scheduler. The MajorMinor frame scheduler has a major frame, and it can contain up to 256 minor frames. Each minor frame can send up to 128 commands. Each minor frame can also switch between 2 blocks of memory. So while it can only send 128 at a time, it has access to 256 commands total by switching in the blocks. There are 2 clocks. There's a major frame clock and a minor frame clock. The major frame will restart at the major frame clock rate. So if it's set to 1 hertz, every second the major frame will restart. The minor frame clock just has to be set fast enough to execute every minor frame before the major frame restarts. Here's an example. The major frame would be this box here. The minor frames are listed here. And then you would fill in commands for each minor frame. You can optionally have a second block ready, and these can be completely different commands. So it supports cyclic and multi-rate commands. Cyclic because it restarts. Multi-rate, as we will see, is you could set up commands that go out 8 times a second, or 4 and 1, all within this major frame. You can put in no-op commands to allow for commands to be transmitted on specific time boundaries. The MajorMinor frame scheduler will send a command on one side of the bus and if it doesn't receive a reply, it will automatically retry on the other side of the bus. And it will also handle error detection. Let's go over an example how to use it. If your application requires 32 commands at 8 Hertz, 16 at 4, and 21 at 1 Hertz, you create a minor frame with the 32 commands that you need to go at 8 Hertz. You create a minor frame with the 16 commands you need to transmit at 4 Hertz, and then another with the 21 commands at 1 Hertz. You set the major clock to 1 Hertz. It'll restart every second. Add 8 copies of the minor frame with 32 commands into the major frame. Add 4 copies of the minor frame with the 16 commands into the major frame. Add 1 copy of the minor frame with 21 commands into the major frame. You simply have to set the minor frame clock fast enough to execute every minor frame before the major frame restarts. So there's 13 minor frames, and the major frame restarts every second. We would need to set the minor frame clock to 13 Hertz. This is what it might look like for clarity. You'd have 8 minor frames with 32 commands, 4 with 16, and 1 with 21. In actuality, you would probably interlace these minor frames before you start the system. Let's see a video and then run some sample code that you can download from our website. Hi, we're here today to talk about 2 different types of bus controllers in the UEI 1553 system. There's a FIFO-based bus controller and one with MajorMinor frames. In sample 553, we see the use of TX FIFO, and that is a FIFO-based bus controller. You set up the command you want, the data if appropriate, and calling TX FIFO will simply send that command. If you want to use a MajorMinor frame scheduler, then we go to sample 553 bus cont. This scheduler will add major frames, minor frames, and allow you to set the frequency of the minor and major clocks. Thus, you have a choice. You can use TX FIFO to simply send a command when you'd like, or set up the major and minor frames to continually send commands at varying frequencies to different RTs. We're going to introduce you to the major concepts involved in setting up the 1553 scheduler by using a small application with 4 minor frames. Actual systems may use these concepts to scale to a much more complex system. Section 1, the major and minor frame clocks. The major frame clock tells the major frame when to restart. If it's set to 1 Hertz, the major frame will restart every second. The minor frame clock indicates how many minor frames can be processed within the major frame cycle. Say the major frame clock is 1 Hertz, which means the major frame will restart every second. If there are 4 minor frames and the minor frame clock is set to 4 Hertz, then all 4 minor frames will be executed before the major frame restarts. If there are 4 minor frames and the minor frame clock is set to 2, then only 2 of the minor frames will be executed before the major frame restarts. Section 2. How to send a command at a certain frequency. In this example so far, each command is sent once every major frame cycle, or at 1 Hertz. In more complex systems, you may need to send a command at a higher rate, say 2 Hertz. To accomplish this, just add 2 of the same commands into the major frame. Section 3. How to set commands to go on a particular time boundary. If you need to make minor frames execute at a certain point in the major frame cycle, you need to add no-op commands. For example, say the major frame clock is 1 Hz and you have 4 commands, but you actually need them to go out at 1/8 of a second boundaries. You will need to add no-op commands to accomplish this. We've introduced you to some of the major components of the 1553 scheduler. There's certainly much more functionality in the 1553 system. If you have any questions, please feel free to give us a call or send us an email. You can look us up on the web at www.ueidaq.com. So when you install our software, we give you samples for all our I/O boards. And in 1553, there's plenty of samples for the remote terminals, bus monitor, bus controller. They're all right here. And today I'll be using a Loopback test adapter. So it ties channel 0 to channel 1. So basically, I can run a complete 1553 system. One channel can be RTs, the other can be a BC, and have an optional bus monitor. This is sample 553 bus cont. It's available in our release, and it's designed to exercise the major minor frame scheduler. As you can see here, we set up a major frame, a minor frame, and we add commands. And very quickly, we just start the system. So we're seeing commands go out. We have a BC to RT command, which is a receive command. So you would see data words. The RT replied with status. Then we have an RT to BC command. So the BC would send a transmit command, the singular command, and we would get back status and some data words from the RT memory. So let's show how easy it is to add more commands. There, we've added 2 more. So we have a receive, a transmit, another receive, and another transmit. Let's make this run a little bit faster. Let's adjust the major and minor frame clocks. There, we've sped up the system. What this code is doing is configuring our FPGA on the 1553 I/O board to send these commands. This application is not responsible for sending them once the FPGA is programmed. It goes off on its own, communicating a list of commands you want sent. If you notice the while loop, we're just reading the bus monitor data. Alternately, you could be checking the returns from all these commands in our bus controller. And you might see, I talked about error checking. I showed you the major errors. Here are all the errors that get checked by the bus controller at runtime. So you could put 2 1553 I/O boards in a system and run 4 independent bus controllers. So you have a major minor frame scheduler running multi-rate commands on an FPGA, and your application would like to know things about it. Some of the common things applications would like to know is, did my minor frame start, and did the last command be transmitted? So we have a BC heartbeat event that can be configured or not, but when it is configured, it will notify your application when every minor frame starts. We also have an IRQ event, and the system designer, the application writer, decides which command will generate this event. You can have many commands generate this event. Typically, people use it on the last command in the minor frame. So again, the IRQ event can be put on many, none, or just one of the commands in the system. So I'm going to show you some code that is basically sample 553 bus cont with asynchronous events added. First, let's see a video, and then I'll show you the software. UEI's 1553 I/O board emulates a bus controller, any or all RTSAs, and a bus monitor. Through our API, you can control these components, read and send data words, and even check status. Sometimes an application needs to be notified of something happening rather than checking for it. To accomplish this, we've implemented event notifications for the following commands and conditions. For instance, when an RTSA receives data, when an RTSA sends data, when a mode command is received, or even when a specific mode command is received. On the BC side, the application can be notified when a minor frame starts, and the IRQ event can notify the application when any or all commands have been sent. An example of this is to use the IRQ event on the last command in the minor frame. When the event is received, you'll know that every command in the minor frame has been sent. There are many more events available through our API. Okay, so this is an asynchronous setup. It has the major minor frame scheduler here. I'm adding commands. I'm adding 30 commands actually. And on the last command, I'll set the IRQ event. We'll take a look at, this is the thread that handles events. And when we receive the BC heartbeat event, will be here in this code, or the IRQ will be here in this code. So let's just change this. So we're seeing the events. The heartbeat occurs every time a minor frame starts, and the IRQ events occur on the last command in that minor frame. This software is available from us on our website. If you contact us, we can help you download the software, point you to these samples, and help you tailor this to your specific application. So in summary, our 1553 I/O board has two complete multi-rate cyclic frame schedulers capable of handling complex 1553 applications very easily. Optional events are there to notify your application of what's happening in the bus controller when it's running on the FPGA. And there's a bus writer if you simply need to send a series of commands. We support many languages and interfaces. I've shown C here today, but there are many more. Thank you for attending. There are some links here for the software downloads, as well as a tutorial page on our website. Okay, thank you for sending in your questions. Oh, can each channel be enabled and disabled independently? Yes, actually, sample 553 has sample code that allows you to do that. Can you dynamically change commands in the BC at runtime? Yes, there's two ways. We have the dual block of memory, so if you set up both blocks ahead of time, you can just simply switch in the second block, or you can overwrite any command in the major minor frame scheduler when you want. Which physical configuration is the smallest? Oh, so we have the UEI net and the 1553 I/O board. So if you would have just one 1553 I/O board in a very small rugged cube. That would be the smallest configuration. Can we convert 429 data and put it on the 1553 bus? Yes, absolutely. If your application knew the 429 data from an external source, you could simply send it through the bus controller out. If you'd like us to handle the 429 interface, you could put a 1553 and 429 board in a system. We would read the 429 data and the application could send it out the bus controller or even through RTs in the 1553 system. You can also do it that the other way. We can take the 1553 data and send it out A-Ring 429 if you'd like. Do we support direct coupling? Yes, we support direct coupling and transformer coupling. How to modify the value of the data words? Well, you could do that dynamically. You can change the values of the data words in the MajorMinor frame scheduler when you'd like. Maybe you take an IRQ event to know that command went and you update the data words. Well, those are all the questions for today. But if you have any more, please feel free to email us or call us.
Okay, thank you, Phil, and thank you everyone for participating in today's webinar. We'll be continuing the UEI Masterclass series at the same time next Thursday. Next week is the last of our 1553 series and the end of Avionics Month. In June, we'll be presenting detailed information on the UEI PAC, our programmable automation controller platform. We'll take a look at OPC and Modbus, and we'll dive deep into LabVIEW. We record every webinar and post the videos online the same day. You can also watch any of our previous sessions either on our YouTube page or on our own webpage, ueidaq.com/videos. And finally, we hope you found this webinar useful and hope to see you again next week. We'll be contacting anyone with unanswered or partially answered questions. And if you need additional support or you've got a suggestion for a future webinar topic, please email us at support@ueidaq.com or just give us a call, 508-921-4600. Thank you again for joining us. And until then, have a safe Memorial Day weekend and please stay healthy.